Welcome to 7th lecture of module 2. The module 2 is on mass transfer coefficients. So, in this lecture we will continue our previous lecture, which is interphase mass transfer. In the previous lecture we have seen that to calculate the flux for interphase mass transfer, we need to know the interfacial concentrations, but the interfacial concentration is not easy task to measure by simple device, or we can say the interfacial concentration is not measurable by simple device. So, we cannot calculate the flux using say k y into y a b minus y a I interfacial concentration, or k x x a I minus x a b. We have seen that we can use the overall mass transfer coefficient concept to calculate the flux. So, N A will be capital K y y a b minus y a star, where y a star is in equilibrium with x a b, and k y is the overall mass transfer coefficient. Similarly, we can use N A is equal to capital K x x a star minus x a b. X a star is the equilibrium concentration with y a b. Then how to correlate or the relations between the overall coefficient and the individual coefficient? How to correlate between overall coefficient and individual coefficient. So, this we will discuss by graphical method. We know that so this is the equilibrium line, and say this is y a I is a function of x a I, this equilibrium line, and suppose so this is the operating line, or this is the slope of these equations. As we know, slope is minus k x k y. Suppose this point is P and this location is x a b and this is y a b bulk concentration, and this is the interfacial concentration where this line meets on the equilibrium line. This is y a I and this is x a I. This y a b, if we draw a line on this, so this is the equilibrium with x a. So, this is x a star, and similarly this is x a b equilibrium with y a star. From this point, so if this is the slope of the line, suppose the slope of this line is m double dash and this is m dash, then at steady state at steady state we can write N A is equal to K y y A B minus y A I is equal to K x x A I minus x A B, and also we can write is equal to capital K y y A B minus y A star. So, from this we can write y A B minus y A I by N A is equal to 1 by K y y A I minus x A B by N A is equal to 1 by K x. Similarly, y A B minus y A star by N A is equal to 1 by capital K y. Now, from this figure we can write y A B minus y A star, y A B minus y A star we can write sum of y A B minus y A I plus y A I minus y A star. So, we will write y A B minus y A I plus y A I minus y A star. So, which is equal to y A B minus y A I plus y A I minus y A star. If we multiply by x A I minus x A B both denominator and the numerator, so this is the slope of this line. The slope of this line is y A I minus y A star divided by x A I minus x A B. So, we can write y A B minus y A I plus m dash x A I minus x A B. Therefore, we can write y A B minus y A star divided by N A is equal to y A B minus y A I divided by N A plus m dash x A I minus x A B divided by N A. So, this is nothing but 1 by capital K y is equal to y A B minus y A I by N A, which is 1 by small k y plus m dash by k x. So, this is the relations between the overall mass transfer coefficient and the individual mass transfer coefficient. In the similar fashion, we can write N A is equal to k y y A B minus y A I is equal to k x x A I minus x A B is equal to capital K x into x a star minus x a b, or from this we can write x a star minus x a b divided by n a is equal to 1 by capital K x. From the geometry of the figure, we can write x a star minus x a b. This is the overall driving force for mass transfer. So, this will be equal to x a star minus x a I plus x a I minus x a b. So, we will write is equal to x a star minus x a I plus x a I minus x a b. So, we can write this equals x a star minus x a I divided by y a b minus y a I into y a b minus y a I plus x a I minus x a b. So, this is 1 by m double dash, and this will be into y a b minus y a I plus x a I minus x a b. Now, if we divide both sides by n a, so this will be n a and this will be n a. So, this is nothing but 1 by k x, capital K x is equal to 1 by m double dash k y small k y plus 1 by k x small k x. So, this is the relations between the overall mass transfer coefficient in terms of the liquid phase with the individual mass transfer coefficient. If the concentration of the solute in the system is very low and if it obeys Henry's law, in that case m dash will be equal to m double dash, which is equal to m, and which we can write H Henry's law constant by total pressure P t. And this relations between the overall mass transfer coefficient in the gas phase will be 1 by capital K g is equal to 1 by small k g plus h by k small k l, and 1 by capital K L will be equal to 1 by h k g plus 1 by K L. So, when h is small, in case of absorption of ammonia in water or HCl in water, in that case we can write 1 by capital K g will be approximately equal to 1 by small kg. And similarly, when H is large, as in the case of CO2 in water, it forms carbonic acid, or oxygen dissolution in water, the H is large. So, from this we can write 1 by capital K L approximately equals to 1 by small k L. Now, the fractional resistance offered by the gas phase will be equals resistance offered by the gas phase divided by the total resistance of the two phases. Which is equals to 1 by K y. This is the resistance offered in the gas phase divided by the total resistance offered by both the phases is capital K y. Now, fractional resistance offered by the liquid phase can also be defined will be equal to resistance offered by the liquid phase divided by the total resistance of the two phases, which is equals to m dash by k x small k x divided by 1 by capital K y. Let us take an example to calculate this individual coefficient, flux and interfacial concentration for a particular system. For absorption of certain gas from an air stream by water, the value of Kg was found as 2 into 10 to the power minus 6 kilomole per meter square second kilopascal. The absorption takes place at 298 Kelvin and at 1 atmosphere pressure. At a particular location of the absorber, the gas phase concentration is 5 mole percent and the liquid phase concentration is 0.2 mole percent. Only 10% of the total resistance lies in the liquid phase. The solutions obeys Henry's law at 298 Kelvin and the values of m is equal to 1.5 when the total pressure is 1 atmosphere. Calculate the individual gas and liquid side mass transfer coefficients, flux and the interfacial concentrations. Now, the data which are given is Kg is equal to 2 into 10 to the power minus 6 k mole per meter square second kilopascal. And we know that capital K y is equal to capital K g P t, which is equal to 2 into 10 to the power minus 6 into 101.3 kilopascal. 1 atmosphere is 101.3 kilopascal, which is equal to 2.03 into 10 to the power minus 4 kilomole per meter square second. And it is given that 10% of the total resistance in the liquid phase. So, 90% of the total resistance should be in the gas phase. Now, we know that fractional resistance offered by the gas phase is equal to 1 by small k y divided by 1 by capital K y. So, which is capital K y divided by small k y. This is given 0.9, 90%. So, small k y will be capital K y divided by 0.9. If we substitute capital K y, 2.03 into 10 to the power minus 4 k mole per meter square second divided by 0.9, which is equal to 2.26 into 10 to the power minus 4 k mole per meter square second. We know that one by capital K y is 1 by small k y plus m by k x. So, m by k x is equal to 1 by capital Y minus 1 by k y, and we know that fractional resistance offered by liquid phase is equal to m by k x divided by 1 by capital K y, which is equal to m capital K y by small k x. So, this is given as 10%, which is 0.1. So, from this we can calculate m by k x is equal to 0.1 divided by capital K y. So, this will be equal to 0.1 divided by capital K y. So, from this we can calculate k x will be m capital K y divided by 0.1 is equal to m is given 1.5 into So, m is given 1.5 into 2.03 into 10 to the power minus 4 divided by 0.1, which is equal to 3.045 into 10 to the power minus 3 k mole per meter square second. So, these are the individual mass transfer coefficient. Now, we will calculate the flux. To calculate the flux, we know the equilibrium compositions y s star is equal to m into x a. M is given 1.5 and the concentration in the particular location is given 0.002. So, which is equal to 3 into 10 to the power minus 3, and y a b is given 0.05 mole. So, N A will be equal to capital K y a b minus y a star, which is equal to 2.03 into 10 to the power minus 4 into 0.05 minus 3 into 10 to the power minus 3, which is equal to 9.541 into 10 to the power minus 6 k mole per meter square second. We know that N A is equal to K y into y a b minus y a I. So, from this we can calculate the interfacial concentration y a I will be equal to y a b minus N A by K y. So, if we substitute, it is 0.05 minus 9.541 into 10 to the power minus 6 divided by 2.26 into 10 to the power minus 4, which is equal to 0.0078. And from the equilibrium relations, we know that x a I will be equal to y a I by m. So, which is equal to 0.0078 divided by 1.5, which is equal to 0.0052. So, these are the interfacial concentration and this is the flux, and we have calculated the individual mass transfer coefficient. So, now we will discuss the material balances to generate operating lines. In general, when there are two phases are in contact, they are in direct contact between the phases in the equipments. So, direct contact among the phases in a particular equipment. In case of flow process, due to transfer of solute from one phase to the other, the concentration in each phase changes along the equipment. So, if it is a batch process, in this case also the concentration change with time. Since the concentration change with time, there is a variation of driving force for mass transfer along the equipments. So, change of concentration produce variation of driving force for mass transfer. How we can follow these changes of concentration through the equipment as the phases flows from one end to the other, and this can be followed. The change of concentration can be followed by material balance. There are three mode of contact, three mode of operations we will discuss. Three mode of operations. One is counter current operation, second is co-current, and third one is cross current. So, let us consider steady state counter current flow. In a steady state counter current flow, consider there are gas and liquid phase, they are in contact, and gas being a lighter component compared to the liquid phase, they flows from bottom to top and the liquid flows from top to bottom. So, this is the location at Z1 and this is some intermediate location any plane, and this is at location Z2. So, at 1 the gas flow rate is G1 and Gs is solute free basis, and Y1 is the mole fraction small y1 and capital Y1 is the mole ratio basis. So, these are the nomenclature which is given. So, gas there is inlet at the bottom and outlet at the top, and liquid in at the top and out at the bottom. So, G1 is the rate of gas in at location 1 in mole per time, G2 is the rate of gas out at location 2 and mole per time, Gs is the rate of gas flow on solid free basis in mole per time, G is the rate of gas flow at any arbitrary location inside the equipment, and small y, small y1 and small y2, these are the mole fractions of the solute in the gas phase at respective locations, and capital Y, capital Y1, capital Y2, these are the mole ratios of the solute in gas phase in the respective locations. L1 L2 and Ls, these are the liquid flow rates, and L, these are the liquid flow rates at respective locations, and small x is the mole fractions of the solute in the liquid phase, and capital X is the mole ratios of the solute in the liquid phase. So, with this convention, if we do the material balance, we can define like G s, as we said, which is solute free basis. G s can be written is equal to G by 1 plus capital Y, and capital Y is equal to Y by small y 1 minus small y, or from this we can write small y is equal to capital Y divided by 1 plus capital Y. L s is L by 1 plus x, capital X. Capital X we can write x small x divided by 1 minus small x. From this we can write small x is equal to capital X divided by 1 plus capital X. The overall mass balance, if we consider the envelope of 1, the overall balance over the equipment which is envelope 1, overall mass balance for envelope 1 for component A, for a particular component A over the envelope 1. This we can write G 1 small y 1 plus L 2 x 2, which is in is equal to G 2 y 2 plus L 1 x 1. So, this is equation 1. The component mass balance over envelope 2, we can write G 1 y 1 plus L x is equal to G y plus L 1 x 1. This is equation 2. Now, if we write these equations in terms of the solute free basis, we can write G 1 into y 1, small y 1 is capital Y 1 by 1 plus y 1, capital Y 1 plus L 2 into x 2 by 1 plus x 2 is equal to G 2 y 2 by 1 plus capital Y 2 plus L 1 capital X 1 by 1 plus x 1. So, this will give G s y 1 plus L s x 2 is equal to G s y 2 plus L s x 1. From this we can write L s by G s is equal to y 1 minus y 2 divided by x 1 minus x 2. Say this is equation 3. So, this equation is the equation of straight line. Which passes through the points capital X1 Y1 and X2 Y2 with a slope Ls by Gs. Now, the equation 2, this equations also you can write in terms of the solute free basis. So, that is G 1 Y 1 plus L x is equal to G y plus L 1 x 1. So, this also will give you G s capital Y 1 plus L s capital X is equal to G s capital Y plus L s capital X 1. From this we can write L s by G s is Y 1 minus Y divided by X 1 minus X. So, this is also equations of straight line and passing through the points x 1, y 1 and x capital Y with a slope L s by G s. This equation is in general relates bulk compositions of the two phases at any location with the terminal concentrations. So, this is called as operating line equations or equation of operating lines. If we plot for the case we discuss, so this is the equilibrium line and this is the operating line with a slope L s by G s and this is the concentration, this is x 2 y 2 and this is y 1 x 1 and suppose this is m and this is n. So, this is the equation of operating line and this is the equilibrium line. So, if the solute transfer from the gas phase to the liquid phase, then the operating line is above the equilibrium line. If gas is transferred from liquid to gas, then operating line will be below the equilibrium line. So, this is also with the slope L s by G s and mass transfer from liquid to gas phase. If we plot the difference between the mole free basis and on mole basis, when we plot solute free basis, the operating line is straight as we have seen, because it is based on L s or G s, which does not change along the path of the travel of the phases in the equipment. Whereas, if we take the quantities G and L, these are changed as it flows from one location to the other in the equipment. Since there is mass transfer from one phase to the other, this G and L changes and hence L by G ratio changes. So, the equations of operating line will be not straight line. So, it will be curved line like this, and if we plot, this is x 2 and this is y 2, this is x 1 and this is y 1. Suppose this is M and N, 2 points, and this is the equilibrium line, and this is the operating line, with a slope L by G. So, the slope is changing if we plot in terms of mole fraction basis. So, the equilibrium line and the operating line both will be curved, since L and G they are changing along the flow paths of the phases. Now, let us consider steady state co-current flow. The notations have their usual significance as we have discussed earlier. In this case, if we consider envelope 1, in this case the flow is in the same directions, both and gas and liquid flows in the same direction from point 1 to point 2. The overall mass balance for component A over the envelope 1, we can write G s capital Y 1 plus L s x 1 is equal to G s Y 2 plus L s x 2, and mass balance over the envelope 2, we can write G s Y 1 plus L s x 1 is equal to G s y plus L s x. And if we rearrange these equations, we can write y 1 minus y 2 by x 1 minus x 2 will be minus L s by G s, and also y 1 minus y by x 1 minus x will be minus L s by G s. So, the slope is negative, and this is the equation of operating line with a slope, operating line with a slope minus L s by G s. And if we plot this is the line and this is the slope minus L s by G s, and this is x 2, this is y 2, this is y 1, and this is x 1, and in between this is suppose x and this is y. So, the operating line will be above the equilibrium line if this is mass transfer from gas to liquid phase. So, if the mass transfer is from liquid phase to gas phase, the operating line will be below the equilibrium line, and this is x 1, this is y 1, this is x 2, this is y 2, and some point in between, this is x and this is y. So, this is also the same slope of minus L s by G s. Now, among these two cases we discussed, that is counter current operations and co-current operation mode, which one is better or which one is preferred? If we consider a given situation, for counter current flow, average driving force is higher compared to co-current flow. Average driving force for mass transfer is lower compared to counter current flow. So, the amount of solute transfer for a given solvent is higher. Solute transfer in this case is lower compared to the counter current flow. And if we consider for the same equipment, the lower flow is required in case of counter current flow compared to the co-current flow, or if we keep the same flow, then the equipment size required is small. So, from all these points we can say that counter current operation is preferred over co-current operation. Thank you.